Hi guys, today I'd like to talk about the Taylor series. And what the Taylor series is a rewriting of functions in polynomial form. And this is useful to make algorithms, or if you ever want to take the derivative or integral of something. Sometimes you can't do it when it's a function, but you can do it when it is in this polynomial form, or it may be easier to do. So we're going to start out by saying that we think sine x can be written like this in polynomial form. And so to show you the difference between the two, I'm going to bring my calculator over here, and you could take your calculator out also. And this is a very popular illustration to show the Taylor series of sine x. If in y1 you put sine x, and in y2 you put this polynomial here, which is x minus x cubed divided by 3 factorial, so that's 3 math probability, and then number 4 for the factorial sign. You're going to add that with x to the 5th power divided by 5 factorial. And then what I'm going to do is I'm going to move my cursor up here to the y2 symbol here, that's a slash, and I'm going to change that slash, toggle it so it's a dark slash. So when I hit enter, it makes a dark slash. So when I graph these two functions, the sine x function is going to look like a light graph, and the polynomial function here will look like a dark graph. So let me go ahead and graph this. There's my sine function being graphed right now, and now my polynomial, this x to the 5th degree polynomial, is being graphed here. And what I'm going to say is this is an approximation of sine x. It really is a good approximation of sine x just between this point and this point, right? Not always. If I tried to find, say, sine of, something big, sine of 7 or something like that, something big over here, maybe sine of 10, it's not going to be, this polynomial will not be a good approximation. But if I wanted sine of, 0.5 or 0.2, it might be a good approximation, right? Because it's a pretty good approximation between these two intervals here, which look like maybe between negative pi and pi. Okay, well, how could I make it an even better approximation? So it turns out if I put some more terms here, and you can see the pattern here, x minus x cubed over 3 factorial plus x fifth over 5 factorial, what may be the next number? Negative x to the 7 over 7 factorial plus what might be the next term? X raised to the 9 over 9 factorial. And of course you could do this for a long time. So what I've done here is on my calculator I've put in extra terms here, and you can see that as you go extra terms, your radius that you converge at gets better and better and better, meaning you can approximate more and more values of sine. Here my convergence was maybe here. That was a good approximation, where this polynomial was a good approximation for sine x. Right, this is the actual sine x. Right, this right here is the approximate. So this is the approximate. This is the Taylor series, which is an approximation for sine x. Over here, here's where maybe the polynomial is a good approximation of sine x, and this polynomial here is this one up here. And then on this third one, I went and I did an extra term here, this x to the 9th term. And so if I look at where this is a good approximation for sine x, it's a little bit wider than this approximation here, and this one's a little bit wider than this approximation here. So it turns out the more terms I go, the more accurate this polynomial will be for sine x. So what we're going to do is think about, well, how do we develop these polynomials? These polynomials are called Taylor series polynomials. Taylor series polynomials. And here is the formula for it. An approximate polynomial, so we call it P, okay? Later on when we make it go to infinity, we might call this T for Taylor series. But it doesn't matter what letter you call it. This is going to be equal to f at c plus f prime at c times x minus c plus f double prime of c, x minus c squared over 2 factorial plus f triple prime c, x minus c cubed over 3 factorial plus, and it goes on. So what you might want to notice is that these numbers are all the same. This is the second derivative, this is raised to the square, and this is 2 factorial. This is the third derivative of f, this is raised to the 3 power, and this is 3 factorial. Now, this is true for when you take the Taylor polynomial about x equals c. And what that means is at x equals c, that's where you're going to get the best approximation using the Taylor series. So if you look at what happens here, if we make x equal to c, if we put x equals c here and c here and c here and c here, what happens is all these terms wipe out to 0, right? All of these terms here will wipe out to 0. And all you have left, these will wipe out to 0. And all you have left is this term here, which means that f of c is equal to that function, whatever function you put here. So the best estimate for the polynomial, the best estimate that the polynomial makes for the function is always at where x is equal to c. So here c was equal to 0 because when we wrote this polynomial, what we did was we centered the polynomial at x equals 0. But the center doesn't have to be at 0. If we wanted to center it somewhere else, let's say out here, so that we could get a more accurate number for sine of 3 pi or something, then what you want to do is make your center 3 pi. So that's what c stands for, the center. Right here, if c is equal to 0, what happens is this is 0, this is 0, your c's are all equal to 0, okay? And so you get this equation right here, this formula right here, and this formula down here is called the Maclaurin polynomial. So the Maclaurin polynomial just means that your center is equal to 0. All right, let's talk about how do we find the Taylor polynomial for sine x? How do we estimate sine x as a polynomial? Okay, well, the way you do that is you make a table. Okay, first you have to memorize this formula, but then you make a table. And let's talk about what our table will look like. Okay, so on the left side, we're going to put f of x is equal to sine x, all right? And then you want to take the derivative of this, and you want to take the derivative all the way until whatever this number says. You want to go into the 5th derivative, or the 5th degree, okay? So the first derivative of sine x is cosine x. The second derivative will be negative sine x, the derivative of cosine. The third derivative will be negative cosine x. The fourth derivative, then we just start putting numbers up here because it's a lot of work to put a whole bunch of apostrophes. The fourth derivative is going to be sine x. The fifth derivative is going to be cosine x. Then right next to it, we plug in the center. Now, what is the center for this problem here? It says a Maclaurin polynomial, so that means the center is equal to 0. So what we'll do is we'll plug in 0 here. And f at 0 would be sine of 0, which is 0. F prime of 0 would be cosine of 0, okay, which will be 1. F double prime of 0 will be negative sine of 0, which will be 0. F triple prime of 0 will be negative cosine of 0, which will be negative 1. f to the fourth derivative at x equals 0 is going to be 0, and the fifth derivative at x equals 0 is going to be 1. All right, then this information here is what we're going to use to plug into that formula we've memorized for the Taylor series. What is the formula for the Taylor series? It is when you're estimating the polynomial. So a lot of times we start with saying polynomial at the fifth degree. Okay, plugging in x, what we get is f at c plus f prime at c, x minus c to the first power over 1 factorial, plus f double prime at c, x minus c to the second power over 2 factorial, plus f triple prime of c, x minus c to the third power over 3 factorial, plus the fourth derivative of c, x minus c to the fourth power over 4 factorial, plus the fifth derivative at c, x minus c to the fifth power over 5 factorial. All right, so this is the Taylor polynomials to the fifth degree. Fifth degree means the highest degree here is 5. Okay, so then what we say is the center here is 0. So we're going to go through, and everywhere you see a c, you'll put in a 0. So 0 goes there, 0, 0, 0, 0, 0, 0. And the center is not always 0. It's 0 for this situation here. And we're trying to find the Maclaurin series or Maclaurin polynomial, so we'll put zeros here. So what this turns out to be is we know all of these derivatives here, right? So we can plug them in. F at 0 is 0, so this number here is 0. We know f prime of 0 is 1, so that's this number here, that's 1. F double prime of 0 is 0. F triple prime of 0 is -1. F to the fourth degree at 0 is 0, and f to the fifth degree at 0 is 1. So now we just simplify this. This is the polynomial of sine x. So what we're saying is sine x is approximately equal to, all right, and then we just write all this down. This is 0. The first term is 0 plus 1 times x over 1 factorial. So that's going to be x. And then this next term here, this third term is 0. So that's just going to be 0. And then plus -1 to the x third power over 3 factorial minus x third over 3 factorial. This fourth term here is 0 times all of this, so this will be 0. The fifth term here is going to be plus x to the fifth over 5 factorial. Well, this is interesting. This is the Taylor series, or I guess I'll call it the Taylor polynomial of degree 5. And degree 5 means that's the largest degree I'm going to. Okay, for sine of x. And does this not look like this right here? This right here that we talked about for an estimate for sine x? It's the same thing. So that's how you get the polynomial, the Taylor polynomial for sine x. And of course we could have gone further if we had found, up to the 6th and 7th and 8th and 9th derivatives. Let's answer some questions about this sine x derivative. Remember, this is an estimate for sine. So what if I wanted the sine value of 1.4? What if I wanted sine of 1.4? Well, I could use this polynomial to estimate it, right? So that's going to be approximately equal to, everywhere there's an x, I'm going to put in 1.4. 1.4 minus 1.4 to the third power over 6 plus 1.4 to the fifth power over 5 factorial, which is 120. 1.4 minus 1.4 raised to the third power divided by 6 plus 1.4 raised to the fifth power divided by 120. And that gives me 0.987. The answer is 0.987485 or something like that. Okay, that's from my calculator. All right, now what is the real value of f at 1.4? What's the real value of sine of 1.4? Let's see how close we get. Remember, this is a Taylor series approximation for using polynomials. And if I do sine of 1.4, sine of 1.4, that's equal to 0.985449, and goes on. How far apart are them? What is the error of my approximation? Let's subtract this from 0.987485333. So my error is about 0.002. So what's my error? It's about 0.002. Okay? How did I get that? I just subtracted these two numbers here. I'll write it down so you guys can see where I got it. This is equal to 0.987485 minus 0.985449. All right, so this is actually an error. And in calculus, when we do errors, we don't have to worry too much about the sign. So we can just do the absolute value of the difference between these two. So the error is symbolized by this expression here. And doesn't that make sense to you? This right here is the actual value of sine 1.4, and this is the approximate value of sine 1.4. So make sure you know this notation, because sometimes on the AP test, they won't ask you for the error. Instead, they'll just ask you for this symbol right here, this expression. And you need to know that this expression is really just the error. All right, what if I wanted to find the approximation of sine at 2.1? Okay, so remember, this is 1.4 and this is 2.1. So I'm getting further away from the center, right? If I remember coming back here, where is 1.4 and where is 2.1? 1.4 is about, say, half of pi. So 1.4 is about right here. Okay, so 1.4, negative 1.4. And 2.1 is a little less than 3, right? So a little less than pi. So pi is here. So 2.1 might be somewhere here. Okay, so what we're doing is we're getting further away from the center. Remember, we said the center is where we're most accurate, or it will be accurate. Okay. All right, so what if we did 2.1 here? So what I'm going to do is say 2.1 minus 2.1 raised to the third power over 3 factorial plus 2.1 raised to the fifth power over 5 factorial. What is that equal to? Let me get my calculator out. Actually, that formula is in y2, right? So what I can do is I can go pull out my y2, so vars y vars function y2, and just plug in 2.1. And what I get is 0.8968. All right, so that is my approximation for sine using the Taylor series to the 5th degree. What is the real value of sine 2.1? Sine 2.1. The real value is 0.86320. Okay, that's sine 2.1. What is my error here? Remember, this is the expression for error. What is the actual value minus the approximation? So this is going to be equal to 0.86320 minus 0.89684. And that's just the absolute value, because we don't care in calculus if it's positive or negative. So I'm going to subtract 0.89684, and my error is 0.0336. Which, if we compare our errors, so let's look at the error here and the error up here, then this error here is larger than this error here, And that's expected, right? Because when we put in 2.1, we were further away from the center, 0. And when we put in 1.4, we were closer to the center, 0. So this will be, 1.4 will be a better approximation than the 2.1, okay? So how does the error compare? We would say the error for P of 2.1 was greater than the error for P of 1.4. And what would happen if we tried to estimate sine of 2.7? What do you think the error would be? The error would be even larger because we're getting further away from the center, getting further away from x equals c. All right, let's do another problem. This problem here says, suppose you have f, it's a function, it has continuous derivatives, they tell you all these derivatives. What is the Taylor polynomial of degree 3 for center at 2? So center at 2 means c is equal to 2, okay? Make sure you understand, center at 2 doesn't mean necessarily plug in your x at 2. What it means is when you write your polynomial, write it with a center at 2. Okay, so let's go ahead and write our polynomial. The formula for a Taylor polynomial or a Taylor series is the polynomial at degree 3 of x is equal to f at c plus f prime at c x minus c to the first power over 1 factorial plus f double prime at c x minus c squared over 2 factorial plus f triple prime c x minus c to the third power over 3 factorial. All right, this goes to infinity, but if we're looking for the polynomial to just the third degree, we will stop at the third degree right here. Now let's go ahead and plug in our c. My c is 2, so this is 2 here, 2, 2. All right, and then let's plug in what we know. We know f of 2 is 3, so what we have here is the polynomial to the third degree is equal to f of 2 is 3, so this will be 3 plus f prime of 2 is negative 4, so this will be minus 4 times x minus 2, the quantity x minus 2, divided by 1, but 1 factorial is just 1, plus f double prime 2, so the second derivative at 2 is 7, so this will be plus 7 times x minus 2 squared over 2 factorial, but 2 factorial is just 2 times 1, which is 2, plus the third derivative, which is negative 5. This will be minus 5 x minus 2 to the third degree over 3 factorial, and you can write 3 factorial, or you can write 6. All right, so this will be the answer for the polynomial for f to the third degree. All right, let's do the next problem. Find the Taylor polynomial of degree n equals 4 for f of x equals e to the 3x plus 2. All right, so when we're given the function, we make a little table, okay? Because the reason we make the table is so that we can get all of these derivatives here. All right, if we're given the derivative, then in a sense, this table was already formed for us. So they pre-made the table here. This was the table. But if we're not given the derivatives, we need to make the table to find these derivatives. All right, let's go ahead and get started. So the first thing we do is we write f of x is equal to e to the 3x. Then we take the derivative of that. So that's 3e to the 3x. Then we take the derivative of that. So that's 9e to the 3x. Then we take the derivative of that. So that's 27e to the 3x. And this says to the fourth degree. So let's move to the fourth derivative. Okay, in this table, right next to it, what we'll do is we'll plug in the center. And the center is right here. This is saying write the polynomial of degree 4 with center at 2. So we use the center when you're forming the Taylor series polynomial. All right, so let's go ahead and plug in the center. So what we have is f of 2 is equal to e to the 6. F prime of 2 is equal to 3e to the 6. F double prime of 2 is equal to 9e to the 6. F triple prime of 2 is equal to 27 e to the 6, and f to the fourth degree, the fourth derivative of 2, is equal to 81 e to the 6. Now what do we do with these numbers? We put it into the Taylor series formula. So the Taylor series formula is, let me pull down my paper. The Taylor series formula is the polynomial to the fourth degree is equal to f at c plus f at c, the first derivative, x minus c raised to the 1 power over 1 factorial, plus f double prime of c, x minus c squared over 2 factorial, plus f triple prime c, x minus c to the third power over 3 factorial, plus f the fourth degree at c, x minus c to the fourth power over 4 factorial, and I can stop there for a degree of n equals 4. So let me go ahead and plug in. Everywhere I see a c, I'm going to put in 2. So this will be 2's all right here. Okay, and then what we'll do is now we just plug in. We know f of 2 is actually equal to e to the 6. We know f prime of 2 is 3e to the 6. F double prime at 2 is 9e to the 6. This one's 27e to the 6. And this one is 81e to the 6. So our answer here is going to be e to the 6 plus 3e to the 6 times the quantity x minus 2 plus 9e to the 6 times the quantity x minus 2 squared over 2 factorial plus 27e to the 6 times the quantity x minus 2 to the third power over 3 factorial plus 81e to the 6 times the quantity x minus 2 to the fourth power over 4 factorial, and that is our answer. And some things I want to point out. One thing students do for some reason is they write the formula for this Taylor series, but for some reason they skip this first term here. They move straight into f prime at c, x minus c over 1 factorial. I know that's because students are really excited about taking derivatives, but I want you to know you can't move into the derivatives right away. You need to actually write f of c first. Okay, so this first term, for some reason, students just totally ignore it, but you need to have the first term, f of c. Okay, and one way I remember it is this is a bad word, fc, right? So you just always have to put the bad word first, and then you can move into your f prime of c's and so on. All right, you guys do this one. See if you can do this one by yourself. Okay, we want to write the Taylor polynomial of degree 6, okay, for the function ln of x, and our center is equal to 1. First, you make a table. So f of x is equal to ln of x. F prime of x is equal to 1 over x, which is really x to the negative 1. F double prime of x is equal to the derivative of this, which is negative x to the negative 2, which is equal to negative 1 over x squared. F triple prime of x is equal to the derivative of f double prime, which would be 2x to the negative 3, which is the same thing as 2 over x cubed. F to the fourth degree is going to be negative 6x to the negative 4, which is also negative 6 over x to the fourth. The fifth degree, or the fifth derivative, will be 24x to the negative 5, which can also be written 24 over x to the fifth. And the sixth degree, or the sixth derivative, is the same as negative 120 x to the negative 6, which will be the same as negative 120 over x to the 6. All right, so I need to make a table. I need to put in the center is equal to 1. So this means f at 1 is equal to ln of 1, which is equal to 0. F prime of 1 is equal to 1 over 1, which is equal to 1. F double prime at 1 is equal to, I'm going to plug in 1 right here for the x, so that's going to be negative 1 over 1, which is negative 1. F triple prime of x, F triple prime of 1 is going to be 2 over 1, which will give me 2. The fourth derivative at 1 is going to give me negative 6 over 1. The fifth derivative at 1 is going to give me 24. And the sixth derivative at 1 is going to give me negative 120. All right, what do I do with all of this? I write a Taylor polynomial, okay? How do I write the Taylor polynomial? Well, I want a Taylor polynomial of degree 6 that's going to be equal to f at c plus f prime at c x minus c to the first power over 1 factorial plus f double prime at c times x minus 1 squared over 2 factorial plus f triple prime of c x minus 1 to the third power over 3 factorial plus f to the fourth degree at 1 x minus 1 to the fourth power over 4 factorial, etc. Notice that when you write the formula, these are all plus signs. Students want to alternate them for some reason. They don't always alternate. Actually, here they alternate. In sin x they alternate, but they don't always alternate. Okay, so the formula is strictly just all plus signs here. I went ahead and took the liberty of putting my c's in here. You don't have to. You can do it in 2 steps if you want to. But what we want to do is plug in for all of our tables here. This value is 0. This value is 1. The second derivative is negative 1. The third derivative is 2. The next one's negative 6. The next one's 24. And the next one's negative 120. So let's go ahead and rewrite this Taylor polynomial. P6 is equal to 0 plus x minus 1 minus x minus 1 squared over 2 factorial plus 2 times x minus 1 to the third power over 3 factorial minus 6 times x minus 1 to the fourth power over 4 factorial plus 24 times x minus 1 to the fifth power over 5 factorial minus 120 times x minus 1 to the sixth power over 6 factorial. And we can look at this and see that there's some more things that we could factor out. First of all, this 0 here doesn't need to be here. 0 plus doesn't have any effect on the Taylor series. Right here, this is actually 3 times 2, right? 3 factorial is really 3 times 2. So if I call this 3 times 2, and this 4 factorial, right, is really 4 times 3 times 2, okay? And this 5 factorial is really 5 times 4 times 3 times 2 times 1. And the 6 factorial is really 6 times 5 factorial. This 5 factorial is really 5 times 4 factorial. So it turns out there's some reduction we can do here. 2 divided by 2, 6 divided by 3 factorial, 24 divided by 4 factorial, 120 divided by 5 factorial. And so what we get if we simplify is P6 is equal to x minus 1 minus x minus 1 quantity squared over 2 plus x minus 1 to the third power over 3 minus x minus 1 to the fourth power over 4 plus x minus 1 to the fifth power over 5 minus x minus 1 to the sixth power over 6. And this is an expression of ln of x, where ln of x is approximately equal to if we go to the 6th degree. All right, AP could ask you another question. They could say, okay, what if you know this p to the 6 right here? What if you already know that? Could AP ask me, what is the second derivative at 1? Or could AP ask me, what is the fourth derivative at 1? Could I go backwards and figure that out? All right, so what you have to know is, first of all, you can't find the second derivative at anything but the center. All right, so given this P6 here, this Taylor series here, if you know that it is a Taylor series, then you know that it follows a certain pattern. That the Taylor series P6 is equal to f at 1 plus f prime at 1 x minus 1 over 1 factorial plus f double prime of 1 x minus 1 squared over 2 factorial plus f triple prime of 1 x minus 1 raised to the third power over 3 factorial plus f to the fourth power at 1 times x minus 1 to the fourth power over 4 factorial, and so on. And so what you want to do is, if you want to find the second derivative, what you do is come up here and see that the second derivative is part of the coefficient, part of it, not the whole coefficient. It's part of the coefficient that goes with x minus 1 squared. So what we do is we say, okay, here's x minus 1 squared. Here's x minus 1 squared. So you match up the x squared portion, all right? What students do wrong is they'll try to match up the 2 factorial portion. That 2 factorial changes depending on things that are simplified, all right? So we can't match up this 2 factorial. What we have to match up is the power series part, this x raised to the power part, okay? And what that tells me is the coefficient here, which is -1/2, okay, is actually formed by this coefficient here, the f double prime 1 over 2 factorial. So we set those equal. So what would we do? We would say, all right, -1/2 is equal to f double prime at 1 over 2 factorial. All right, 2 factorial is just 2. So what I have is f double prime at 1 is equal to -1. All right, so that's what I get for my second derivative. Is that correct? Well, let's go back up here. My second derivative at 1 is -1. Okay, let me go see if I can find my fourth derivative. To find the fourth derivative, again, I have to match up things. All right, so I'm going to find the x to the fourth power on my Taylor series. I'm going to match that up with the x to the fourth power on my series for ln of x. All right, then what I do is I set these coefficients equal. The number one thing students do wrong in these problems is that they'll say f to the fourth power at 1 is equal to -1/4. Now, what did I do wrong? This coefficient is not f to the fourth of 1. This coefficient is f to the fourth of 1 over 4 factorial. And this coefficient here is -1/4. You set the coefficients equal. 4 times 3 times 2 times 1 is actually 24. So maybe I'll just say 4 times 3 times 2 times 1 is equal to -1/4. This is going to be equal to f to the fourth 1 is equal to -4 times 3 times 2 divided by 4. The 4's are going to cancel out. So what I get is f to the fourth of 1 is equal to -6. And let's see, is that true? Let's go back to the fourth derivative at 1. The fourth derivative at 1, indeed, it was -6. All right, so AP expects you to be able to go forwards on the Taylor series and find the Taylor series. And it expects you to be able to go backwards too and find the derivatives associated with these coefficients. If you're given that P is equal to this expression, it's a second degree Taylor polynomial for f about x equals 0. Can you tell me what the signs are of these coefficients a, b, and c if you know that this is your graph? Okay, well, let's think about what we know about the Taylor series. if this is a Taylor series, okay, then this formula came from this formula up here, all right? And we're doing about x equals 0, so we actually can use a Maclaurin formula, okay? So the Maclaurin polynomial here is actually this formula right here. So let me write the Maclaurin polynomial. P2x is equal to f at 0 plus f prime at 0 times x plus f double prime at 0 over 2 factorial times x squared. So if I look at these two formulas here, this formula here and this formula here, what I see is my a is actually the same as f of 0, and my b is actually represented by f prime at 0, and my c is actually represented by this coefficient here, f double prime at 0 over 2 factorial. And all I want to know is, can you tell me if these are positive or negative? Well, these are all happening at x equals 0, right? So here's my x-axis, here's 0. So right here, f at 0, is it positive or negative? It's positive, right? This point right here, this y value will be positive. So I know that a is actually positive. I'll say because the y-intercept is positive. All right, what about f prime at 0? Is the derivative at 0 positive or negative? Well, the tangent line at this point looks like this, right? Is that tangent line positive or negative? Because the slope of the tangent line is the derivative. So is this tangent line positive or negative? It's a positive slope. So what we know is b is actually positive because the slope is positive. Okay, or f prime at 0 is positive. All right, what about this right here, f double prime at 0? So at this point here, is my second derivative positive or is my second derivative negative at this point? Yeah, the second derivative at 0 is actually negative, right? Because this is concave down. So remember, when f double prime is negative, f prime is decreasing, and f is concave down. All right, so if f is concave down, this second derivative is actually negative. 2 factorial is positive, okay? So c is actually going to be negative. Why? Because f is concave down. Or you could say the second derivative at 0 is actually negative. Okay, so that's important to understand. Let's look at another problem. Suppose the function f of x is approximated near x equals 4 by a third degree polynomial. So this means that c is equal to 4. Okay, it doesn't mean that we plug in x equals 4, but it means that when we develop this polynomial, we use the center at 4. So find the value of f, find the value of f prime, find the value of the second derivative and the third derivative all at 4. Okay, so what we have to know is what the original Taylor series says. The original Taylor series says this is f at 4 plus f prime at 4 over 1 factorial, x minus 4, plus f double prime at 4, x minus 4 squared over 2 factorial, and plus f triple prime for x minus 4 to the third power over 3 factorial. Okay, so what does that mean? That means that when I have a 2 power here, this term is associated with my 2 power here. You got to look at the powers. Please do not look at the 2 factorial. That's not going to help you. So what that means is that this coefficient right here is equal to the coefficient right here. All right, so that tells me that f double prime at 4 over 2 factorial is equal to negative 5. This means f double prime at 4 is equal to negative 5 times 2, which is negative 10. Let's look at the third degree problem here. So if I look at the third degree here, okay, this is saying that this coefficient with the third degree, x minus 4 third degree, is equal to this coefficient right here. All right. Now what students do wrong is they'll ignore the 3 factorial. They'll just say the third derivative is equal to 8. They'll just say the third derivative is equal to 8, and that's incorrect. It's actually this entire coefficient, which is the third derivative at 4 over 6. That's what 3 factorial is equal to 8. So that tells me that the third derivative at 4 is equal to what? 48. So I have found the third derivative, I have found the second derivative, and let me see if I can find another number. This 2 here is not associated with any x raised to a power, right? So the question is, should I set this 2 equal to this f of 4 here, or should I set this 2 equal to this coefficient here? Yeah, it should be this f at 4. Why? Because there's a missing term here, right? The term that's missing here is x minus 4 raised to the 1 over 1 factorial, f prime at 4. This is equal to 0. There's a missing term here. So that means that this 2 is not associated with this x minus 4 term, but this 2 is actually associated with this constant out here. So what I know is f at 4 is equal to 2. And I think I have found everything. No, I haven't. I still need to find the f prime at 4. And what do you think the f prime at 4 is? Well, in this problem here, this f prime at 4 must have been what? Right, this right here must be 0, okay? Because there's no term here for f prime, okay? So what I know, if this makes sense, what I know is I set this right here equal to 0. Essentially, I guess I don't have to put this here. This is what this is here. So I set this equal to 0. And what I'll get is f prime at 4 is equal to 0. So does f have a local maximum, a local minimum, or neither? Well, let's think about this. Remember what we talked a long time ago about the second derivatives test? The second derivatives test says that if the second derivative at some point c is positive and the first derivative at that same point c is 0, then what we know is that there is a local minimum at that point, x equals c. And if the second derivative at c is negative and the first derivative at that same point c is 0, then we have a local maximum at x equals c. All right, so what we're doing is we're saying the derivative at 4, the second derivative at 4, we know is negative 10. And the first derivative at 4, we know is 0, right? So what does that tell us is happening at 4? At the value 4, we have something that's concave down, and this derivative here is 0, okay? First derivative is 0, and we have something concave down. So what's happening there is that we have a local max, all right? So the answer here is we have a local max at x equals 4 because the second derivative at 4 is negative and the first derivative at 4 is equal to 0.